Assalamu alaikum, dear students, and welcome back to Seismology. I wanted to do a lecture today that talk a little bit about some of the basic associated with some of the fundamental aspects of seismology. And in the theories that drive the very occurrence of earthquakes, why they occur, how they occur, and then talk a little bit about some of the different types of seismic sources or faults that generate earthquakes, and then a little bit about how seismologists today and even some engineers like me can use some prediction models to try to predict the size or the geometry of an earthquake. So today we are going to cover things like elastic rebound theory, different fault types, whether they are crustal or subduction zone, and then of course earthquake size. So let's begin with the elastic rebound theory. This is one of the most basic theories associated with seismology and earthquakes, and it's really quite simple. Imagine if you were holding like a brittle stick just right out in front of you, not with one hand but with two. You were holding both ends of the stick. Now imagine, as you are holding both ends of this stick, you move your left arm slowly and your left arm down slowly, and you are holding the ends of the stick. You are keeping that stick rigid as you are just translating one arm up and one arm down. So it's look like of this right here, where you start to bend and deform the stick, but eventually what's going to happen is you are going to fracture that stick. if that if that stick is brittle, it will fracture. If it was like a young stick or was an old or brittle, then it will probably bend or flex. But we are going this mental experiment with a stick to represent another material. It's very brutal, and that is rock. Rock is very brittle, at least rock that is in the lithosphere is very brittle. So when it begins to strain and strain, it can deform quite a bit actually, but eventually you strain it enough and it will fracture. And once it's fractured, it releases all of this energy, and all of that energy then it is sent out in the form of seismic waves. So it's that sudden fracture of the rock that causes the release of that energy that we know as a seismic waves in the form of body waves. Typically, okay, so again this is the elastic rebound theory presented in 1911 by Red. So it's been around for a little while, so part of this theory too is detail that goes into it, and we know that when movement occurs on a fault, it's all due to stress being locked up in different places on the fault. And usually there's a places where the stress is just concentrated and causing the fault to lock up. Now as stresses get transferred around to what we call expertise. Expertise are points of stress build up. So think of these as like jack spurs or places where the plates or the crust just lock up. So as stress get transferred between these plates of stress concentration of expertise, and it begins to lock up again, and it will lock up until the strain gets so large that all of those expertise break, just boom, and then you get this big rupture, and then you get strain, a big release of energy along the fault, and then all that energy is released and a new expertise form. and events, it's lock up again after an event. Interestingly, as stuff, all the stresses are trying to work themselves out, and everything's trying to find a new balance and a new equilibrium. That was distribution of stresses are across the expertise, which lead to what we refer to as aftershocks. Some people ask me in the past, why do aftershocks occur? We have this big earthquake and then it feels like the ground never stops shaking for days and sometimes for weeks. Well, that's because the ground is trying to find a new equilibrium and a new expertise haven't locked up yet, and that's the main reason. So another misconception that a lot of people have is that if an earthquake happens and they know that they live next to a fault, and this could be a really big fault, lots of time people think, oh, if that whole fault goes, then I am going to be in a big trouble. But the reality is that entire faults rarely rupture all once. Usually, instead, they rupture just in parts of the fault. So, usually in small sections that we call segments. So, a fault will divide up into what we call segments. So, okay. So, if I have, for instance, this big long fault that looks like this, but paleoseismologists may dig and they find that this section of the fault tends to rupture on a certain frequency, but this section on the fault ruptures on another frequency, and this section of the fault ruptures on another frequency. So we might have then 1, 2, and 3 segments of a fault, and each segment can behave independently of the other segments, or not. I mean, there's a lot of evidence that sometimes more than one segment can go, or the rupture of one segment could lead. Okay. One segment could lead to the rupture of another segment. So there's no hard or fast rule on these, but just understand that faults are usually divided into segments. So if a long time passes before for a certain fault segment ruptures, then you know that expertise are locked up and stress is building up on that fault segment, and eventually that fault segment is going to rupture, and this is what we call a seismic gap. So a seismic gap is a place, a fault segment along a known fault where we haven't had seismic activity for a long time. So this is a figure out of Kramer or geotechnical earthquake engineering textbook. I love this figure because it really shows what's going on. What we have here is a graphical representation of San Andreas Fault through about half of California. So we have here distance. Okay, so you can see it start up near San Francisco, up near the northern edges of the fault, where it flies out into the Pacific Ocean, and then it ends down here past a little past file. Okay, so as we are headed down towards southern California, so what this file represents, every single one of these dots that you see on this figure here represents a recorded seismic event, recorded earthquakes, and its location on there. And though each of these boxes represent the depth below the ground surface that earthquake was traced back to, using what we talked about in our previous lecture by the triangulation method. Okay, so what we have here on the part, up here on the first part, is all of the recordings that occur 20 years prior to the 1989 Loma Prieta event. So you see, we had an event on this segment of the San Andreas. How do I know? Well, look at all those dots. So we know that there was an earthquake, and on that segment during that 20 years period, and it looks like on this segment too, there was an earthquake, because we see lots of dots. But check out these other segments. Here a couple dots on this segment here, and a couple dots on the other segments down here. Well, check this out. In October of 1989, the Loma Prieta earthquake happened just south of San Francisco, near the San Jones area, near Loma Prieta. Actually, this plot down here represents the main shock, which is this big circle right here, and then all the other aftershocks that were recorded from the Loma Prieta earthquake. So if I take all these dots and I transfer them back with their cousins up here in the first plot, you can see that we would fill in a whole bunch of dots in the seismic gaps. That's right, that's we call it a seismic gap, because it means that there was a gap of data before the earthquake happened. So once this data moves up here, we still have a gap in the San Francisco segment. And interestingly, we had a gap in Parkfield. But I thought that was pretty cool. In 2004, the Parkfield event happened. So this segment also get filed up with its dot, all of it seismic activity that happened. That leaves one more seismic gap remaining. That's right, the affair San Francisco event on a San Andreas that falls a log and loaded, and it's ready to go. Now this may seem like a random thing to talk about, but I do want to mention it just briefly, and we will talk more it later. But when a fault ruptures, it doesn't just rupture all of at once, like the fault was still, and then the next millisecond it's all rupture and it's done. What happened is a section of a fault. Let me go back here. Okay. Let's say our fault again, and let's say this segment right here going to rupture. So what happened is rupture begins where one of the major asperities break. So let's say it's right there. Then as stresses rapidly distributes to other asperities on the segment, they started breaking too, so you could have a propagation of the rupture in both directions. And in one direction from where the initial asperities broke, so as it's almost like ripping a zipper open, and so you can get this ripping effect of the segment down from where the rupture initially occurred. Okay. So as every time a rupture or every time a rupture occurs on the fault, there's having asperities break. It releases a giant amount of energy in the form of body waves that begin to transmit and move through the surrounding rock, and that's what this figure down here represents. Let's say here it's at time equals 0, we have our initial rupture, and this ringing around the initial rupture is that the ring of energy as it starts to emanate from the original source, and then due to stress distribution another asperities breaks in this direction. So here right here where I have colored this with the red dot, that was the initial rupture, and the asperities next to it now broke, so energy is emitting from that rupture as well. But we still have the energy that's still emitting from the first asperities rupture. The second leads to a third asperity rupture, and the third leads to a fourth asperity rupture, the fourth to the fifth, and so on. So, and every time there's a new rupture, as this rupture starts ripping out the segment of a fault, more energy is released. Now notice what happens. Each of these rings just represent the spreading out of the energy, the spreading of those body waves, and in 3 dimensions. Notice how in the direction of the fault rupture, we get a staking of energy. All those waves start piling up in the direction of the rupture, and you can tell that because all those circles representing again that the spreading energy, look how they just start piling up. That is a huge conglomeration or constructive interference of waves that produces a huge amount of energy. So this zipper ripping effect of faults is going to produce greater ground motion in what we call the fault normal direction, meaning that if my fault is aligned, and well, let's go back to my figure. We are going to see that the waves are emitting out from a fault like this. As the waves comes out of the fault, if I take the axis that is parallel, perpendicular to my fault origin, we call this normal fault. The way that parallels to the fault rupture is what we call, yeah, you guess it, a fault parallel. Okay, there is some data, quite a bit of it, that suggests that ground motions are larger in the fault normal direction. So meaning that if I were to line up a building or something, that it weak axis aligned with the fault normal direction, the fault parallel direction, this fault normal versus fault parallel direction is what we call directionality. Okay, directionality of ground motion. So we talk about this stacking of energy. Okay, so going back to this constructive interference of the waves in the direction of the fault rupture is what we call forward directivity is so what we talk about with the fault alarm on fault parallel, that's directionality. uh, Directivity all has to do just with stacking of the waves, has to do with the constructive interference. Now, interestingly, notice what's going on, by the way, in the opposite direction of the direction away from all rupture. Notice how this spreading out of the waves. Okay, so we can get deconstructive interference in those instances, but spreading out of the waves also prolongs the ground shaking. So the ground shaking may not be as intense in the backwards directivity direction, but in the forward directivity direction, ground motion can be very intense and very powerful. And in general, if you are within about 10 kilometers of eruption fault, you can feel the effects of this forward directivity, particularly to high period structures or structures that have high periods of vibration or low frequency of vibrations. So these would be structures like bridges, water tanks, tall buildings, what kind of thing. So directionality, directivity, those two things are what we refer to as near source effects. Near source effects, we will talk about this in future classes. Okay, so one thing I like to remember about directivity, it's easy, it's a way to help me remember. Its directivity is just like a Doppler effect. This is something you can look up on YouTube or in the internet. You will see it with like police sirens. So if the police car driving towards you, the pitch of the sirens of the police car will always sound higher pitch, and then when the car drives past you, if it sounds like the pitch is changing, it's almost like the siren change, but it didn't. All that change was the velocity of the sound waves relative to you. So when the car was approaching you, the velocity of the waves were faster. The waves were stacked together. When the car passes you, the waves are stretched out. It changes the pitch of the waves. So elastic rebound theory is important, and it's important because we can attempt to quantify then what this theory, the amount of work that's performed when an earthquake occurs. Why in the world would we ever want to compute that? Well, because work is another way we can describe energy, and so if we can quantify how much work an earthquake or went to an earthquake, that we can quantify the amount of energy released. So to do this, we are going to compute a term called a seismic moment. And here's the equation for the seismic moment, that that n sum naught is the seismic moment. This little mu right there, that represents the rupture strength of the rock on the fault. So think of this is like a peak compressive strength of the rock. So that I guess would be the peak shear strength of the rock that we have an area. This is the rupture along all the fault. So what would this look like? It would look like something like this. I'm not good with drawing. I'm not an artist, okay? So let's say I have a cross section of the fault. It's going to look something like this right here, the fault. Okay, actually let's just bring all this way down to go. Okay, so here is the fault. The fault extend down like that. Okay, so you can imagine that we have this block, this big block right here, and we have this upper block right here, and this big block on the right. This one can move up and down, and this one stays on the left, will stay. So if that's case, that if you want to compute the surface area for the rupture, all it is the area of the fault where the two planes slide against each other. So in this particular instance is going to be this surface area right here. So this is going to be equal the surface area of the fault rupture. So you have to start thinking of faults in 3 dimensions. You have to start picturing the fault plane, and it goes down into the earth's surface, and when the movements occur, there's going to be friction between both sides of the rock and the soil on that plane. Wherever there's friction occurring, that's the surface area of the fault. So that's our right here, the D bar is going to be the average displacement that occur along the rupture area. So how much slip occur on the rupture? Okay, now seismic moments, there's different ways to describe energy. For instance, we could put it in terms of joules, or we can put it in terms of hertz. 1 joule, of course, is 1 Newton meter of work. Generally, when we are talking about seismic or on moment, we use units of hertz, which is 1 times 10 to the minus 7 joules. Okay, so that was all for today's lecture, and we will continue this lecture in our next class. So if you guys have any questions through it, you can ask. Anyway, thank you for the participation. Thank you so much.